The name of this video is the Electrostatic Field. Suppose we take two point-like charged particles in space. These two particles are both fixed in an inertial reference frame. For simplicity, IF, inertial frame. The first particle is our source particle, so it's the source charge. So this one, let's place it, let's say, here. This is Q1, located at a point in space, capital Q1. So all source charges hereafter will be indicated with capital Q letters. Capital Q1 is the location of the charge Q1. So this is our source charge. This is fixed in an inertial reference frame. We have another fixed particle in general here. This particle is our test particle with charge Q0. All test particles will be located at a point in space called capital P. So capital Q for source, capital P for test particles. While this test particle is also in general fixed, we can move it while keeping fixed at for each experiment. We can move it anywhere we want in space. This remains always at the same location. At each instant, of course, at each of these points is fixed in this inertial reference frame. And so, because of this test particle can span, so it spans the entire three-dimensional Euclidean space. And by doing so, it allows us to test, this is the key word, to measure the force F due to the source charge Q1 at any point capital P in space, which again is fixed for each experiment in its own inertial reference frame. So this is our test particle, which allows us to measure, to test this force. Now in this case, where everything is fixed and simple, we can use Coulombs law. From Coulombs law, we know that this force F at point capital P, the point of the test charge, is given by Q0, which is the test charge, times 1 divided by 4 pi epsilon naught times Q1 divided by the distance between these two particles, this distance here. Let's call it R vector between Q1 and capital P. So it's R Q1 capital P square, Coulombs law. And finally, we need our direction, which is U Q1 capital P. Let's do this one in green, just to remind ourselves. This is the unit vector U Q1 capital P. What I'm about to highlight in yellow, this quantity here, this is what, by definition, we call, by definition, the electric field E at point P, or equivalently, more mathematically, the electric field E at this location R Q1 P. This is our electric field. The electric field, the electrostatic field to be precise, because nothing is moving at this point in time, is given by this quantity, and so we just factor out this Q0 and the remaining quantity in Coulombs law is called the electric field. And this is simple because we are just considering two point-like particles in space which are fixed in an inertial reference frame. For example, if I were to consider just a simple positive Q1, so when I do a full dot, I assume that it's positive, and actually let's use the same nomenclature, the same color coding as we've done in the beginning. So positive it was sulfur, so we do with this color. So this is a positive charge, source charge Q1, and this one is a negative charge and source charge. So negative, I do it an open dot and I do it in red. So in this case, in the case of a positive charge, the field lines, this is due to Faraday. If you use again some powder, you can use minimum sulfur. In fact, you will find out that this powder arranges itself in this configuration. And it tends to be expelled from the positive particle. Why is that? Because, by definition, we always choose a Q naught equal to plus 1 Coulomb. So if you choose a Q naught of plus 1 Coulomb, obviously we have a repulsion because the test charge is also positive, and that's why with a positive test charge and a positive source charge, these field lines, which are due to Faraday, they go again away from the source charge. So these are Faraday lines or field lines. Okay, in the case of a negative charge, since the test charge is still plus 1 Coulomb, in this case, obviously, the test charge, instead of being to go away from the source charge, will go towards the source charge. So it will be attracted to it along all these lines, etc. Of course, you need to do these arrows everywhere. Now, interestingly enough, by doing a 3D rotation, so let me write it here so it's more clear. By doing a 3D rotation, we obtain the field lines everywhere in space, and this is said to be a central field with this specific type of symmetry. So we'll come back to this in a few videos. All right. Now, you can have a look at the appendix video called Appendix Cartesian Field. If you look at this video, Appendix Cartesian Field, there I give you a calculation more in detail of how to express, for example, the electrostatic field in this configuration in a Cartesian coordinate system. So here I will just limit myself to give you only one of the three components of a Cartesian coordinate system, O, X, Y, Z. In this case, for example, the X component of the electrostatic field is going to be equal to 1 over 4 pi epsilon naught, as always, times, in the numerator we have Q1, our source charge. We need to have a direction, so you need to be able to write, see the appendix, the unit vector along the x-axis, which is going to be, in this case, x, the x-coordinate of point capital P, minus the x-coordinate of point capital Q, source minus charge. This goes along the x-axis. And this quantity has to be divided by something which I call d to the power 3/2, the usual 3/2. And what is this d? D is a little bit more complicated. It's nothing but d square is given by xp minus xq, same as here. Quantity square is the Pythagorean theorem in 3D. Plus the same for y and the same for z, zp minus the zq quantity square. Okay, and if you look at Coulombs Law, of course, you still get the power 3/2, the typical power 3/2. So see the appendix for the details of how we derive this. All right, so now we know a little bit about the central field. Okay, and we know it also in a Cartesian coordinate system. The next interesting item I want to discuss, and very important, is the case of, instead of one single source particle Q1, capital N. Now I want to use capital N source particle. So instead of one, I have capital N source particles in space. So in this case, for example, let's make a sketch. We're going to have, let's say, a charge here, Q1 at point capital Q, is a source, so capital Q, Q1. Here I will have a charge Q2 at a point capital Q2, eventually dots a charge QK, my index. Capital QK is the point where this charge K is located. And finally, the last charge, which will be Q capital N at point capital Q capital N. So N source charges in space, which again, in the first situation, let's consider that these charges are fixed and known. So let me actually say, it's better to say known and fixed. So we know them and we know that they are fixed. So we know the charge distribution and we know that it's a fixed charge distribution. So this is a known plus fixed in an inertial reference frame charge distribution. Known plus fixed in an inertial reference frame. So if this is the case, so we have a known and a fixed charge distribution, in this case, we can simply write down the force at any point capital P, where we place a test charge Q naught. So this is our point capital P. So we want the force at this point, our test charge, as always. So what is the force at this point? The force due to Coulombs law at point capital P. Now, here we only used Coulombs law. Here we use Coulombs law and the superposition principle because we have a set of charges. So we need to do the same thing, switch all of them off except for one, and then superimpose all these effects. And so we just do a sum. And so we're going to have Q naught, which I factor out as here. But then I'm going to have the sum over the index k, which goes from 1 to capital N, of the charge qk divided by the vector distance between rqk and capital P. So now we need to specify the index. Instead of 1 is k, square, Coulombs law. And the unit vector will be uqk p. So I'm just generalizing this concept. Now in this case, we can define the quantity which I'm putting here, which I'm circling in yellow. This quantity, we define it as the electrostatic field E due to the kth particle at point capital P, which we can also rewrite as the field E at the position R, Q, K vector T, similarly to what we've done here. So again, the difference is that in this case, we used Coulombs law plus the superposition principle. Where PR stands for principle in this case. Okay, so let me give you down here a quick example. For example, for two particles. So suppose that we have a positive particle here and a negative particle here. So let me sketch the field lines. Let's do them in red, for example, in this case. So typically, here I've done yellow for positive and red for negative, but typically I do in red all forces. So now let's move to this new convention. We do red for all forces. So red in red is the field lines, which again, with some powder, I can find out according to Faraday's approach. So in this case, if I have a positive test charge of 1 Coulomb, it will go along this line between these two charges. If I place it somewhere here, it will accelerate in this direction. And then if you use this powder, you will find out that the field lines look like this. And eventually they branch out like this. To come back here. And in the extreme case, they come back in this way. And of course, they are symmetric with respect to this axis. There is a symmetry. They are symmetric because of Coulombs law. So they are symmetric, so I can rotate them to find them everywhere in the three-dimensional space. In particular, this construction is called the electrostatic dipole, which is extremely important, and we will need it particularly in 342 to study dielectric materials. Okay, so this was the simple case where we knew the distribution of the source charges, and those were also fixed in an inertial reference frame. That's the simple case. Suppose that instead we are dealing with a situation where we do not know, so we have an unknown charge distribution of source charges, but still these source charges are fixed in an inertial reference frame, inertial frame. Under these conditions of unknown and fixed charges, we need to resort to the operative definition of the electric field, which is an empirical definition. Operative def, or definition, def stands for definition. So in this case, since the charges are fixed in space, the source charges are fixed, well, in this case, there is an independence from the charge Q naught, and this will become clear in the next point. Therefore, we can define operatively, that is empirically, the electrostatic field E at point capital P as the ratio between the force F due to Coulombs law at capital P divided by the test charge Q naught, and so we have independence from the test charge. Okay, this is very important. This becomes even more clear when we have the most complicated scenario, which unfortunately happens to be the most common in real life, where we have an unknown charge distribution, and these source charges are free to move. So we have an unknown source charge distribution, and the source charges are free to move in space. Well, in this case, you cannot arbitrarily place Q naught, so there is no independence from Q naught. And why is that? A typical example is the following. Even though we didn't study conductors yet, we discussed a little bit about this in one of the first videos. We will come back to this particularly in 342 when we will study the method of images. But for now, suppose to have a semi-infinite conducting slab. Okay, so this is a semi-infinite conducting slab. Let me write it here. Semi-infinite. Why is it called semi-infinite? Because it extends to infinite here to the right hand side. And it's made of a conductor like copper, so conductive, and it's a slab. Okay. Suppose to have this scenario, and suppose that this is uncharged. So it's in the neutral state, so it's uncharged. Obviously, under these conditions, if I pick a point here, capital P in space, at this point capital P, which is my test point, obviously there is no charge anywhere in space, it's all back in here and there is an uncharged conductor. I expect the field, the electrostatic field at this point to be obviously equal to 0. Right? There is no charge anywhere. But in order to measure it, in order to find this electric field, I need to use a test charge, which is our positive test charge Q naught. So let's say that now we place here a positive test charge Q naught at this point in space. Well, even though, again, we'll do this when we will study the method of images later on in 342, you already know from one of the first videos an important phenomenon called electrostatic induction. So when I have a conductor, like the aluminum foil in the electric pendulum we've done in one of the first videos, and I place some, let's say in this case, a positive charge next to it, since the conductor is characterized by free charges, which are the electrons that can move in the lattice here. So what will happen is that there will be some positive, some negative charge distributed on the face of this conductor. And in fact, it will be distributed in this way. So it will be, the sum of this charge will be the same as Q naught. So if this is plus Q naught, here we're going to have that the overall charge here will be minus Q naught, but it's not localized in just one point, it's distributed on this face of this slab. Okay, the slab is like, it's basically, just to make sure that we're on the same page, this is the face of the slab. There is vacuum here where I measure the field. This is the conducting face. And here there is conducting material everywhere, okay? So that's the way you need to look at this picture here. So as it turns out, the negative charge is not localized just in proximity, just in front of this Q naught, but is distributed on the surface. And of course, there is more charge in the proximity of this Q naught, so here, and less as far, if I go further from this charge. This is clear from Coulombs Law, because I go further and further, so there is less electric force acting there. Okay. So we have now this scenario. So now if I were to test again our field at this point P in space, as soon as I have in a realistic scenario, so this is realistic, this charge Q naught, well, clearly I have a charge distribution which I didn't have originally, so I perturbed the electric field, which now is going to be clearly different than zero. And again, in 342, we are going to calculate it in detail. And this obviously is a question mark. And this is because, why do we have that? Because Q naught results in a perturbation. Okay, luckily, in real life, typically we begin with a situation where we have vacuum here, a conducting slab, where we place on it, let's say, some sort of, usually I don't want to measure just something where there is nothing in vacuum. I'm making an experiment where I want to have an electric field. So typically, I'm going to have some positive charge here distributed somehow on the surface of this conducting slab, okay? So I have a positive charge, let's call it Q. When I use a test charge Q naught, this on top superposition principle, on top of this positive charge, which I put this positive charge on the conductor, this test charge will also induce by electrostatic induction this red little charge, which will sum algebraically with the positive charge. So, in your opinion, when this test charge does not perturb too much the experiment? Well, when Q is much, much larger than my charge Q naught. Okay, which we can typically do in experiments. So, in other words, the operative definition of electric field under these conditions becomes a limit. So we want to compute, we want to measure empirically, E at point capital P by performing the limit for Q naught. This is mathematically, we write it to go to 0 plus, it has to be positive because it's plus 1 coulomb typically, but now we don't want plus 1 coulomb when everything is known and fixed. Now we want to make it as small as possible, okay? Really, this is the condition you want to fulfill in real life, okay? But this is the math associated with this condition. Mathematically, we express it in the limit of the ratio between F, which we measure with the test charge, at point capital P, divided by Q naught. This type of limit is called a macroscopic limit, macroscopic, because in mathematical physics, this limit, of course, is not like really a mathematical limit, it's a macroscopic limit, where, again, the key condition is this. So macroscopic really means this condition here. That's really what macroscopic stands for, okay? So that's the real physics of this problem. Also, there are some caveats, and the caveat, where caveat in Latin means warning, and is very much used in science. So the caveat is that there is charge quantization. So there is charge quantization and so in fact we cannot pretend to have a Q naught smaller than the electron charge in absolute value. We cannot have it because the charge is quantized and the smallest charge is the electron charge. Okay, but this is a very important operative definition of the electric field. So that's the way you should do it, okay, with this macroscopic limit. Okay. All right. So in this video, what did we learn? We learned several things. The definition of electrostatic field, that's the first thing we look at. And we look at it in the case of two known, of course, point-like charge particle in space. One was a source fixed in an inertial reference frame. The other one was the test charge. We use Coulombs Law to find the definition of field E, which was independent of Q naught. Then we refined our definition a little bit, and we did it in the case of an unknown charge distribution. Well, we generalized the case of capital N particles in space, so where we use both Coulombs Law and the superposition principle. Then we go to the case where we have this distribution of particles, but this distribution is unknown, but yet fixed in space of the source particles. So the source particles, we have many source particles, capital N, where they are distributed, we don't know, but they are fixed in space. Then in this case, there is independence from Q naught, and we can use this operative, this empirical definition of the electrostatic field. The most complicated case, which is the most realistic one, is when the distribution of charges is unknown, of source charge is unknown, and plus they are free to move, like in a conductor. In that case, we need to use a macroscopic limit, which is the last thing we discussed. Good.